Okay, hello. Thank you for coming. I'd like to introduce Jacob Brackett from One Medical. Please give him your attention and respect as you go through his slides, and please refrain from questions until the end.
Great, thanks. Great. Cool, yeah, my name is Jacob Brackett. I'm an application security engineer at One Medical. I'm here to talk to you today about some research we did as part of our vendor security program, which is attacking radiology information systems. So you may have seen in the news that medical devices are kind of a hot topic in the security world right now. You may have seen other talks or read about some high-profile attacks that have been really announced and talked about recently. Medical devices are definitely becoming a real attack vector for ransomware, for criminals to gain a foothold into hospital networks or other medical networks. The FDA has actually stepped in to issue some guidance and regulation in the space. It's definitely a hot topic in the security world for sure. But this talk is not about medical devices. What this talk is about is the medical information systems that power these devices, that they send their data to. It's where all the data lives. The patient data is sent to a centralized location. It's kind of the golden egg, the treasure trove for attackers. If they're able to gain access to this system, they don't just get access to the information stored on a single medical device, they're able to get access to all of the patient data. Great, so what are we gonna talk about today? At a high level, we're gonna look at an example hospital setup. We're gonna talk about the DICOM protocol, and we'll get into what that is a bit later. And then we're going to talk about how attackers can leverage that protocol in order to attack these information systems and gain access to them. Great, so let's say you are a hospital and you've purchased one of these for the first time. This is an X-ray. It's meant to do chest X-rays. The patient lays down and they make an image of the patient's chest. You've set up your room. You've got lead-lined walls. You may notice something might be missing from this picture. There's no place for a doctor to actually go in and take a look at the image that came out. All there is kind of the camera, if you will, the X-ray device itself. So what you may have to do is figure out a way for that device to send its data outward in order for doctors to look at that. So first step, maybe you route it to a local computer, but maybe you want something that scales. So if you have a hospital network across the country, so maybe you set up something like this. So here is kind of an example. We've got your X-ray machine there on the left. You've got that laptop that a provider is viewing images on. It's serving as kind of a gateway or a router that you'll send your image to that initial on-site place because the X-ray itself is in a lead-lined room. It can't send it directly to the internet. You probably don't want your medical devices connected directly to the internet anyway. So you've set up some sort of intermediary. Maybe you've locked that down. And then that gets sent to your shared imaging cloud. If that's, maybe that's owned by you if you're a huge hospital network. Maybe that's owned by a third party that you've hired out for doctors to go in. And teleradiology is what that's referred to when you have other doctors going in and doing, if you're a smaller company, that's probably what your setup looks like. You've hired contractors that actually go in and do your imaging. Cool, so before we talk about that, let's get into some definitions. I mentioned DICOM earlier. What that stands for is Digital Imaging and Communications. It is the protocol, it's the standard for medical imaging transfers, no matter what type of image, whether it's an X-ray, CT, ultrasound. If you've gone to urgent care and got some sort of medical image taken, likely that image was translated into DICOM and sent over the internet. It's both a file format and a network protocol, and we'll talk about both of those elements later. The next topic we're going to talk about is a PACS, or a PACS system. That stands for Picture Archiving and Communication System. It's basically the web UI, where it provides diagnostic quality images, allows the doctors to go in and actually make their diagnosis. All their annotations happen in that application. It's where the actual diagnostics happen, and that may be on a web server somewhere that you can browse to the internet. It might be internal on an actual laptop, but there is a PACS system that your doctor will be logging into to perform their work. And then finally, we're going to talk about radiology information systems, which is kind of related to a PACS in that a PACS is a part of it, kind of. It's the higher level, the business logic side of the PACS. So whereas the PACS is where you go in and view images. The RIS is where you go in, manage provider schedules. It allows you to click at a certain appointment time and then view the images that were associated to that appointment. Cool, so now you're a radiology expert, you know all the terms. Let's look at our diagram from before and take a look at what that actually looks like. So we've got I'll introduce one quick term here. The modality is your actual device. It's your X-ray, your CT, et cetera, whatever that device might be. That's referred to as modality in DICOM. That would be talking DICOM. So either DICOM, raw DICOM, which is unencrypted, or DICOM over TLS for some more modern devices, although it's usually a very modern device if it's speaking DICOM over TLS, locally over your network. To a DICOM gateway. In this case, it's a Raspberry Pi. We've seen that setup, or it's maybe a Windows computer, something a little more sophisticated. But at the end of the day, that has to get into your centralized RIS or PAC system. So that is done over the internet, either over a VPN, which is the common, more traditional way to do it. But more and more, as more systems are going into teleradiology, that doesn't necessarily work if you have to set up a VPN to each of your 100 clients, and some of these clients are very small. And TLS is kind of sufficient, so a lot of them will just set up DICOM over TLS, or maybe they forget to set up TLS, but they have DICOM over TLS set over the internet to connect to the RIS system. So the images are sent encrypted, hopefully, over the wire over the internet. Great. First, let's talk about the DICOM network protocol. So first off, what are some things you can do with the DICOM network protocol? They're kind of broken down into different composite operations. The main two we're going to talk about today, and there's more, are cfind, which is kind of your generic query retrieval service. It's kind of how you execute search operations. If you want to pull out patient data, you can use cfind to do that. And then the next operation we're going to talk about is cstore, which is your ability to upload a DICOM study. So that's take a DICOM file, take an image that your X-ray is doing a cstore to that system eventually. There's a few other, like cprint is one, cmove, a few operations that would be kind of database operations. So let's dive into what that actual protocol looks like. It's a classic kind of client-server model. There's two components. The client is referred to as the service class user in DICOM, or the SCU. And then we have the service class provider, which is the server in DICOM. So it's kind of the initial handshake period happens where the client asks for an association. We'll dive into that a little bit later. The service class provider either accepts or rejects that association based on what was provided. And then once that association is established, you've got that channel of communication. In this case, we're doing a cfind, so that client makes the cfind request for the data that it wants. And then the server is, the SCP is responding with all of the cfind records that match whatever the client had requested. It sends that final one with a special flag to indicate that it's done. And then that association, it can be closed. And so there's kind of this session that happens as part of referred to as an association. Cool, and so let's dive into that association process. You're security-minded, so you're probably thinking, what's going on here? So there's three items that a service class user is sending with that association process. So the first is the called application entity title. Basically, it's a 16-character host name that's configured when the SCP is set up, the service class provider, the server is set up. And so that has to match, the client sends it, and that has to match with what the client had said. So you're talking to the right person. And then the calling application entity title is also specified. You have to identify yourself with your own host name, your application entity title, or AE title. And then finally, the presentation context is, it's basically the data format. It's what operation you're going to do on the server to make sure that the server can support it. And then, based on those three fields, the service class provider responds with an accept or a reject. Those are the three things that are sent. You may be thinking, where's the authentication? We're talking about host names. Well, that's not built into DICOM. So basically, the only authentication that happens for a DICOM association is a check to make sure that the called application entity title, so that the client knows who it's talking to, the host name, it matches the application entity title that was configured when the service class provider was set up. You know the host name of the server you're talking to, in some ways. And then sometimes that calling application entity title, how the client is identifying itself, is checked against a list of recognized devices. So below, here's the class from an open source, now defunct PAC server called Clear Canvas. Here's the class association verifier, and you can see that what's doing at the comment there is mentioning that it's checking against a list of configured calling application entity titles to make sure that it's a device that it knows it's talking to. So we now know everything we now know everything to set up an association and start querying a server. So what does that look like? This is using a Python library, an API for DICOM called PyNet DICOM for the network protocol. We're going to query a patient name of star, so matching any patient record that the server has. We're going to initialize our AE title with an AE title of hacker. Obviously, the server isn't checking that calling AE title in this case. And we're going to call that association, or the server, with an AE title of gateway. And so let's say that gateway matches the configured SCP, what it was set up with, that application AE title is valid. So the server will respond, and then if we're printing the records as we receive them, here's what that might look like. So there's 3 different patient records. Since those all match star, that the server will respond with every record that it has for patients. So AE titles are the main portion of authentication for DICOM. So kind of how realistic is it to guess an AE title? Well, it turns out that these aren't really passwords. 16 characters for a password, alphanumeric, doesn't sound too bad, but consider that these are often made to be readable and recognizable by someone that's looking at it, so human readable. So they're configured with names like One Medical, if that's who your client is, or One Medical dash 46789, if that's if you want to add some random values at the end to make it a little bit harder to guess. Or they're configured with default values. So gateway could be the AE title for your DICOM gateway, the router that we talked about. Or you have something like find SCU for the service class user that's doing a cfind. So some kind of default values. Also, you may want to find a way for on the web portion of your PAC server in order to easily disambiguate between different clients. Let's say you set up a DICOM server and you have 100 clients that you want to send records to. That server has to route images to the correct place. So what you can do is configure 100 different application entity titles that are all valid for your DICOM server, but route to different clients. So it's slower, lowers the attack surface for what you can actually pull from records if you're able to guess one of those. But now the ability to brute force, now you have basically 100 valid passwords almost in your system. And then let's say you have the web UI portion where doctors actually have to go in and select different information in order to let's say they're logging in, they have to figure out which client they're authenticating to. So what we've actually seen during some testing is that some PAC servers will actually expose the application entity titles to that web UI, sometimes before authentication. So you have to select the application entity title that you want to log into before you authenticate. And so the attacker right away could get a list just by browsing to your PAC's web server of every valid application entity title for your system. So that can cause definitely problems for associating. Or, of course, you just forget to check them at all. So there's this research done in September of last year of some Australian researchers that were able to pull out DICOM records that were not checking application entity titles at all and were left exposed completely on the internet. So they were just able to download some DICOM viewing software, download all the images, look at all the patient information, and look at all those images in DICOM. So let's say you've come across a DICOM server, you're either able to guess the application entity title, or it's just sitting on the internet exposed and you kind of want to see what it can do. Well, it turns out DICOM doesn't have a nice little help function. So when you're talking to a DICOM server, there's no way to just get it to spit out what operations it supports. So you end up having to make requests with all the things that you want to do and see whether or not your association was accepted or rejected. And that negotiation happens during that third field in the association, that presentation context. Helpfully, PyNet DICOM has a dictionary. It has some built-in presentation context, which are basically lists of actual operations, so they're more human readable. It's things like move presentation context or store presentation context, where they correspond to the actual composite operation that you're trying to do. So you can actually use those and in a simple Python loop, just request 6 or 7, I think there's 16 in total actually. If you want to enumerate everything, send that many association requests, see if you can see which ones are either accepted or rejected by the server, and that's how you know what operations you can actually perform on that server. So cfind is obviously dangerous. That's the way you can query patient records. If you are configuring a DICOM server or a PACS server set up on the internet, you do not want cfind. So let's restrict that. DICOM allows you to restrict certain operations. Let's only allow cstore. What could go wrong? Let's talk about DICOM files. That's the second half of the DICOM protocol. It's both a network and a file protocol. This is the header of a DICOM file. Basically, all a DICOM file is a JPEG image with kind of a fancy hat, a nice header there that's got some metadata information about what the image was actually taken. So this is generated by your modality. So let's say we're taking an X-ray image. The provider that would take that image beforehand would enter in the patient ID from their electronic medical record system, their name, the physician's name that's doing the study. They would enter the series number, some IDs that can tie multiple images taken in a single session together, so that the PACS system can take 10 different images asynchronously and then tie that into one single DICOM study, so you can kind of see a time lapse of different images or different angles across the body. So that's kind of how the DICOM file protocol works. If you put on your offensive security hat for a second, you can see that these are generated by a machine, usually, but they are user-generated value. So potentially rife for injection attacks, especially for web frameworks that may not expect DICOM information to actually be user controllable. If you're developing a PACS system, you may not realize that you have to actually sanitize user input that was pulled from a DICOM study because you implicitly trust the devices that you connect, your medical devices that connect to the system. They're the only thing that can route to it. So let's dig into cross-site scripting as an example. We're going to use PyNet DICOM, which is a sister library of, we're going to use PyDICOM, which is the sister library of PyNet DICOM to work on files. This is how you can use it. We're going to download a file, a test file from DICOM library. We're going to read that file in. We're going to set that modality, which is the identification. This would say like X-ray or CT for the different device. That's your identification. We're going to set that to our cross-site scripting payload. Next, we're going to save that file, make sure that actually gets written to disk before we send it off to the server. So with just a few different method calls, we've got our malicious DICOM file. Next, we're going to use an open source tool called DCMTK. We're going to use the store SCU, so the cstore service class user. We're going to call the server AE because we've guessed the AE title or it's not checking. In this case, it's just localhost, but we're going to upload that file, that test.dcm file, that malicious DICOM file. The association is valid, and so the cstore request completes successfully. Now we're going to look at it on the provider side. So let's say this is our open source defunct PACS system called Clear Canvas. We're going to log in with our super secure credentials, admin. We're in. We're going to ignore that last pass. We can remember that one. We're going to search for new studies that came in. Maybe this is our queue. We double click on it, and then that payload file fires. So cross-site scripting. We've bypassed all that authentication. We haven't had to brute force any providers. If there was 2FA configured, which this server allows you to do, we've bypassed that. Great. So let's talk about some kind of lessons learned and next steps. Let's say you've set up an X-ray device on your network, and you protect that. You make sure that it can only send to valid, so no one can create a reverse shell on that and send back to their own systems. The only thing it can talk to is your PACS system. Well, clearly you're not entirely safe because you can upload malicious DICOM files to that with injection payloads that get routed. You have to make sure that your PACS server is actually following OWASP 10 best practices, and make sure you do your due diligence when choosing a PACS system in order for your providers to log in and do their data. We talked a lot about DICOM and authentication. it's worth noting that in the new versions of the DICOM standard, that there's this new concept called a user identity negotiation, where they've kind of realized that AE titles aren't really authentication, and they don't want to, instead of building something on top of it, here's something that the protocol actually supports. You can actually use a Kerberos service ticket or a SAML assertion if you have SSO configured in order to log in and send images to your DICOM server. So you can have your X-ray authenticate to a single sign-on as a machine account, and then before it uploads to the server. Remember though, if you're using a username or just a username and passcodes, I'm not sure how much I would trust my medical devices that I've set up to actually store username and password securely, or in a way that those devices don't get compromised. So as much as you can abstract and remove that authentication piece so that no actual passcodes or hard-coded data is stored on your actual medical devices, the better. And then finally, a note for all you blue teamers out there, understand what protocols are on your network. DICOM, if you're configuring a hospital network, DICOM may be missed or not monitored by your tools. So make sure that your tools can interpret DICOM and look for malicious activity. If your server suddenly starts sending a cfind response with every single record, potentially you have problems. So make sure that you're actually monitoring those networks. Just make sure you're not logging patient data in your logs and storing those unencrypted. Just make sure all your best practices are followed with those logs, because again, this is PHI that you're dealing with here, protected health information. So there's higher standards around those. Great. Thank you.